There we go. So quick review, Bernoulli trial, fundamental experiment type that we get especially in computer simulations, where you have a binary outcome, either success or failure, hit or miss, some type of description like that. Each trial in the experiment is assumed to be independent from all the other trials, and each of the trials has the same probability of success. We'll just call it P. Now it's called the Bernoulli trial, but the distribution is the binomial distribution that describes the probability outcome. And these, if you do any kind of experimentation with computer simulations for systems, right, there's all sorts of metrics that come out as Boolean metrics. Simulation is primarily what I do, but there are physical experiments, right, they can be described with the same description. So teaching statistics, this is a common question I was asked after my classes. So we have a little quick discussion. How many simulation trials are you doing right now? Oh, we're doing about 100. And what kind of accuracy would you like to get? I'd like to get 1%. And so I go look in the books, I go through the calculations for confidence intervals, and I say, well, you need somewhere between 2,000 and 10,000 runs per data site to get that 1% accuracy. And there'd be some grumbling and they'd go away and I'd never see them again. I never liked the answer because I'd look at the data and your data tends to look something like a response surface very often. You're not doing one point in isolation, you're doing something in a response surface. And immediately when you look at that, your mind is drawing isocontours. So I know there's gotta be a way to use the neighbors to incorporate more information and to reduce the size of the data. And I played with this for, I tried different things and I get disgusted with myself because it was becoming more complicated than the problem I was trying to solve, and I'd put it in the trash and go on. Well, one day back in about 2014, somebody asked me to solve this problem because their customer insisted that their simulation plan incorporate this kind of solution. And they just don't want any method, right? They want a statistically validated method that has some science behind it. And so I just started thinking about this, more critically. All right, so I pulled up the usual suspects, right? Polynomial regression for ordinary least squares, looked at splines, looked at logistic regression, and the red marks here are my personal marks on why those are not necessarily the best techniques for somebody who's not a statistician. Because the people asking for help, they weren't statisticians, right? These are engineers in a program that have to solve a problem because their customers insisting that they use statistics to solve it. So that was my take on these different methods that I knew about at the time. Their take was these are all complicated. I don't want something that complicated. I need to run hundreds of these tests. I would like to automate them. You do a continuous integration pipeline, even back then, right? This is all too complicated. I don't like it. I don't get it, right? Kind of an aside, the issue I have with polynomial models is these kind of cases. So the example one, you see a hole in the data. Not just a little hole, that's a very deep hole where there's almost no performance in this particular system at that location. It's very hard for a polynomial to fit that of any reasonable order. Example two, there's a discontinuity in the way the system behaves. There's some decision that happens at X around 0.4 where there's a different algorithm at play. It's making a different type of decision and you get a discontinuity in the surface. And polynomial models don't like discontinuities either. So I was worried in particular about any of the polynomial-based methods and those concerns. So one day I'm on Wikipedia. I'm chasing the Wikipedia rabbit, clicking on pages, going around, and I come across kernel regression. I start reading about it. I'm like, why do this already? I didn't know it had a name. I didn't know there's any science behind it. And so I started reading about it, and thinking about for this problem that I had. Right, if I have Bernoulli data, I can put it in as data sites, pick a kernel function, and just basically do the smoothing average. And it's good everywhere, right? It's interpretable. I can use different size data sizes. It doesn't care where the data sites are. And so today, many of you use like Latin hyperspaces as your simulation design. Works fine with those, doesn't require classical design, has all sorts of these benefits. And so I started playing with it, looked at the kernel functions. Turns out that economists use this a lot. And so they've got lots of papers. So this is a table one of them made that I hijacked here. Lots of different kernel functions. Some of them are local, right? They have very confined spaces that they operate in. I prefer the Gaussian just because it's nice and smooth. They're relatively equivalent, and so you can pick whichever one is makes you happy. If you want to be optimal, right, you pick this Ipinakov one. But it doesn't matter what data you have. The data itself doesn't usually drive your choice here. And I just say that because some people see Gaussian and say, well, that's one, you only use that with Gaussian data. And I'm like, no, it's any type of data, that you can use that with. Here's an example, kind of a contrived example. So truth model is a very classical textbook S function. That's the green line. The red dots are simulation samples from a 25 sample Monte Carlo. There's a lot of data sites in this example, 400 of them across the range. And we just run this kernel. The kernel is to scale in this photo. So you can imagine that kernel just slides across the data and you just average in a local region and you get the blue line, which you see is remarkably close to the true value, the true state of nature, as well as it's nice and smooth. So that's how it works. And not necessarily in practice, but that's a nice ideal situation. Shows you what it does. But what we're really interested in is confidence intervals and power calculations. And so in this case, as an example, let's say it's the 80% region or higher is what the requirement is that you have. And so you want to be able to calculate a confidence interval. And so I did that. And what I found is that the confidence interval is a lot better than I was expecting. And so in this case, with 25 samples at each of the data sites, I'm meeting a fairly tight confidence interval of 4%. And if you go back to my first slide and you do the math, right, this shouldn't work out. So what's happening? Well, that averaging function is increasing the effective size of the Monte Carlos, right? So you're getting this gain factor based on your kernel function and the bandwidth of the kernel function, because you're averaging a region, which is exactly what I was looking for. And it's, it's a very simple function to implement a kernel regression. And so this is an approximation, so it's only good in regions where you're on the slope. It's not good in regions where it's 0 or 100. But you can see the average here is somewhere around 555 is what we're getting for this particular data set, this particular bandwidth. And so that's why it works, is getting better confidence intervals than you would expect for the small Monte Carlo size. It extends to 2 dimensions. You have choices. You can do separate kernel functions for each dimension and a separate bandwidth for each dimension. Or you can take a vector approach. Use one kernel function, but do something like your Euclidean metric. You still have to, you still end up with a bandwidth for each dimension that you have to divide by. But you can do, surface fit like I've shown there to the right. So here's an example of that original data set I showed early on. You run it through the kernel function, and you can see that it does a really good job of smoothing out in the 2 dimensions. The hole maybe is not as deep as we would like it to be. If you look at the original data, you can see the hole is deeper in the data. And we've seen the truth model, we know that the hole is pretty deep, but it does a pretty decent job of smoothing it out. So that's what I was looking for. Finally found it after years of looking for it, found what I was looking for. And the other benefit was that the people I was doing this work for accepted this as a tool. So we like it. It's simple, it's easy, I understand it. And so they actually have used it in their requirement documents. So what's the downside, right? This sounds too good to be true, and it is. Kernel regression always has a bias. And here's an example. There's about 1,000 different curves here from a Monte Carlo analysis shown. I've shown the 95% confidence interval bounds and where that data should fit. And you can see there's a little bit of a tilt on the left end versus the right. And you can estimate that tilt. If you look up papers from Hartle, I believe is one of the people who's written a lot of books on this, right? They'll go into analysis and do some Taylor series expansions, and you can get an idea of what that bias should be. And so for this particular example, it's a fairly simple formula. You can see there's a second derivative in there. And so you'll be thinking, I'm mathematically inclined, the second derivative of like a line is going to be 0, so there's going to be no bias for a line. So what did you say, always a bias? Well, I found when you give a non-statistician a tool, and you tell them there's some exceptions or special rules, they get absorbed in those special rules and they try to turn their problem to fit that. And I don't understand the mentality, but I see it happen again and again. So I try not to give them that opportunity to try to go down one of those special roads. So it sounds like a very downside, but there's a very interesting comparison I read in one of the articles I'm kind of repeating here, which is in a parametric model, the bias comes from the fact that you don't know the model, right? You always have to specify a model when you're working with a parametric model. And so as you get more data, unless you improve your model, add more model terms, do some regression analysis, look at the residuals, figure out what those model terms might be, you end up with a fixed bias based on your choice of model. And you can keep adding more and more data, and that bias doesn't go away. Contrast that with kernel regression. As you add more data sites, you adjust the bandwidth based on the data sites, your bias will get smaller and smaller. The trade-off is if you look at regular regression, you get the 1 over n phenomenon on how quickly your variance shrinks on your estimate. It seems to be about 1 to the n.8, 1 over n.8 for the kernel regression. So you're making a trade-off of bias versus variance when you use kernel regression. So I haven't told you yet, how do you pick H, how do you pick N? And so to find that out, we need to consult some statisticians, and I consulted the 3 bears, right? So on one side, if you pick too big a value of H, you will underfit the response, and you'll get estimates that are biased because of that. At the other extreme, if you make H too small, then you start following the data, and your curve is riding it, and it's very ugly. And what you're looking for is the parsimonious model, right? The model that's the best model fit in between that. What you're trying to find. When I talk about the 2 cases, the underfit case is almost always obvious, right? Remember, we don't know what the true state of nature is. We don't have the green curve to make a judgment. So when the data looks red, you're like, yeah, I don't want that. That's bad. What I've seen in the field when people use this is they always underfit, right? If you give them control of H, they will always underfit. And why is that bad? Well, if you're trying to verify some requirements, now you're underestimating yourself. You're penalizing yourself by doing that instead of using the best, the parsimonious model. And so, when you're doing requirement verification, that can really hurt you. The other thing that happens is, in this case, they wanted confidence intervals out of this tool. And when you underfit, your confidence interval bounds don't work anymore because the bias enters into the data. And so your confidence interval bounds aren't actually bounding the error anymore as well. So how do you solve this? Well, you go to your classical method, which is validation. 2 common approaches to validation. One is you take part of the data and you reserve it and use that to verify your model fit. The other one is you use some of the internal data. They often call them folds, and you try different selections of this. The one I like to use is press, because it's very easy to calculate. And press is basically you take one data site, and that's your holdout. All the other data gets used to fit. And so I've illustrated this here. You see a point PI, which is the data held out. You see the point P parentheses I, which is what would the model fit predict for that point. And you look at that difference, that residual, leaving that one data point out. You do it for all the data points, and you add up the square values of those. That's press. A very simple validation method. That looks like a lot of work. And if you study the ordinary least squares, there's a trick to computing press that makes it a lot easier. Turns out there's a similar trick for kernel regression. It makes it a lot easier. It's still 2 loops, but it's a lot easier to compute it using this penalty function. So here's an example of computing press. You see a nice minimum value. You also notice I used a logarithmic scale for my bandwidth, and that's definitely recommended to do that in this case. So press is not enough. What I found is if you don't look at your residuals and do a residual evaluation, for certain problems, you'll get yourself, look at the optimum press value and say, okay, that's it, I'm done. But then if you look at the residuals, they will tell you that you're still overfitting the model. And that happens sometimes, especially with small data sites, or when you've got a very steep curve, and it's very hard to get data sites on that curve. So showing two extreme example on the right here, where it's underfit, right? And you can see it's underfit because when you look at the left and right halves of the curve, you can see that they're clumped. And that's just, it's just the bias introducing that behavior. You want something like on the left where it's a nice random distribution, half above 0, half below 0, and no preference for the left or right side. So did some trades. Again, this is kind of a toy problem I did it on, but it illustrates a general point we learned, which is if I have a fixed number of experiments I can run because my computer cluster only has so much capability, I have a choice. I can do lots of data sites, or I can do very large Monte Carlos. And it turns out the trade is basically driven by the slope and the curve. You want to get at least 4 points on the slope of the curve in different regions. More is better. And so it turns out that this technique prefers smaller Monte Carlos, a lot more data sites. And we found that this applies to other things. Like if you're going to build a neural network, this also applies as well. You want to get those points on the curve itself. You can even go to the extreme of just running one Monte Carlo point and doing everything as a data site. I'm not sure I'd recommend it because I've seen weird things happen. There's weird perturbations you get just based on luck of the draw of the particular data sites you have. So I wouldn't recommend it, but it is something you can do. It is a possibility with this tool, and it handles it. So in summary, demonstrated this tool that I found, and we're actively using it, and it's working. It is a smoother, right? So if you're looking for interpolation between data sites, this is not your tool, right? This is a smoother. It's going to smooth the data. And you have to pick the bandwidth. If you don't do a good job of that, then all the benefits you think you're getting, you're not going to get. And then in addition to that, this idea that, we've been going down the road of running large and larger Monte Carlos. I work in programs where we're running 1,000 sample Monte Carlos. And this tool is suggesting that that's not the right direction. Once you hit somewhere around 50 for binary data, you're running enough. And you really need more data sites are beneficial. That's it.
Oh, we're done well early, so time for plenty of questions. Yes, Jeremy.
I'm not quite sure I follow the difference between a data site and a Monte Carlo.
Okay. So a data site would be your experiment variable settings, right? So
yeah.
Downrange and altitude. Monte Carlo would be the runs you run at that particular setting. Right, so you might, especially in a simulation, you'll run multiple, simulations. In each simulation, you draw parameters, you draw, random values for your measurement errors, like if it's a time simulation of a, of a system, right? So that's a Monte Carlo in our terminology when we talk about simulations.
Okay, got me. Okay.